So in the previous video, we discussed the basics of ionic formulas and naming ionic compounds that only involve simple ions of individual elements that we can predict their charges from the periodic table. So in this video and the next one as well, we're going to kind of expand on that into other kinds of ions that exist. So this video is about what we call polyatomic ions. And if you think about kind of breaking those words down, it pretty much means what you think it would. Poly as a prefix generally means many or multiple. So polyatomic is saying that there are multiple atoms in this ion. So polyatomic ions are just groups of atoms, groups of connected atoms that together have a non-zero charge. So within a polyatomic ion, the atoms are actually connected by covalent bonds. Sorry. So within the ion is a group of atoms. Those individual atoms are connected by covalent bonds, but because this thing as a whole, this group collectively functions as an ion, polyatomic ions bond to other ions via ionic bonding. So when polyatomic ions are involved, we can actually have compounds that involve both ionic and covalent bonds, that when we have a polyatomic, that group as a whole is connected to the other ions in the compound by ionic bonds. But within the polyatomic ion, we have covalent bonds as well. And again, we're going to be talking a lot more about covalent bonds later in the unit. For now, we just know they exist. So with polyatomic ions, this can either be a good thing or a bad thing, depending on how you look at it. There's not a lot to understand beyond what I've just kind of put forth. They just sort of are what they are. So on the right side of your screen, you see a list of common polyatomic ions. This list is copied and pasted from the back side of your periodic table, so the periodic table that you've been using in class. If you flip to the back of it, there's a bunch of information on there. Most of it you don't know what to do with yet, but on the left-hand side, you will find this exact list of common polyatomic ions. So they just kind of are what they are. They're called what they're called, and they have the charge that they have. There's not a lot of being able to predict what charge is going to happen for a particular group of atoms when you stick them together. So basically you just need to be able to kind of utilize this list. So other than that, kind of recognizing a polyatomic ion when you see one, they function the same way as any other ion in an ionic compound. So on this list that you have, the left-hand column is the name of the ion. So you will notice that a lot of them have things in common. Many of them end in the suffix "ate." That is generally indicative that you are looking at a polyatomic ion. For the most part, the "ide" ending is reserved for elements, though there are a few exceptions. You'll notice amide, azide, and cyanide here. What the "ide" ending actually means is that there is no oxygen in that ion. So that applies to single elements, and it applies to a few polyatomics as well. But you'll notice that most of the polyatomics have oxygen involved. So for those, we use a couple different endings. Most of them are going to be "ate." A few of them are going to be "ite" instead. So most of these are also negatively charged, so the vast majority of the time polyatomics are going to appear as the anion. The one exception to really be aware of for now is the ammonium ion. So you're given the formulas here along with the charges. So whatever is written as a superscript to the right of the formula is the charge on that ion. And you'll see that there are only 2 cations in this whole list. And hydronium is not one you're really going to see in this class. Hydronium appears when we talk about acids and bases, which is something that we say for Chem 2. So the only polyatomic cation to really be aware of for now is ammonium is NH4+. Everything else here is negatively charged. So in terms of how they work in compounds, like writing formulas or naming them, nothing really changes, with one kind of small exception. So let's look at a couple examples. Let's provide the names for some formulas. Let's do KMNO4 and NH4 Br. Sure. So if we want to name these things, just like we did with other compounds, you're going to name the cation and then name the anion. The only thing to be aware of is you have to kind of recognize a polyatomic when you see it, and go find the appropriate name from your list. So pretty much any time that a compound has more than 2 elements for the purposes of this course, for an ionic compound, it's going to involve a polyatomic ion. So in this case, we see we have potassium, manganese, and oxygen. We've got 3 different elements here, so that's kind of a sign that this is probably a polyatomic ion involved. And specifically, the polyatomic is the MnO4 is going to be our anion. So to name this compound, we name the cation, we name the anion, just like we've done before. So our cation is potassium, and if we find MnO4- in my list, I find that that is the permanganate ion. So we would call this compound potassium permanganate. But the second one, this one's a little bit tricksy. That ammonium ion is our cation. So the NH4 is our ammonium polyatomic cation. And these ones can be a little bit tricky because when we talked about how do we distinguish between ionic compounds and covalent compounds, most of the time your signal that something is ionic is that it involves a metal. But you will notice that this compound does not involve a metal. So ammonium NH4 is kind of the one thing to really be on the lookout for that can trip people up, because this is all nonmetals. It kind of seems like it should be covalent, but actually, because NH4 as a group of atoms functions as an ion, this is actually an ionic compound. So as long as we recognize that, we can go find that polyatomic NH4 is known as ammonium. So we name our cation first, just like we always do, and then we name our anion. It's just a bromine as a negative ion, so we change that ending to "ide." So this would be ammonium bromide. So if we want to provide formulas, go in the other direction. I give you a name. Let's do sodium sulfate and calcium nitrate. So when we're writing formulas, we need to consider the charges on our ions. So again, for the polyatomics, the charges are given to you here as part of the formula for that ion. So for sodium sulfate, we can look up sulfate in our list. It is right here. This has the formula SO4 2 minus. Sodium we can look up on the periodic table and find that it is in group 1, which means that it likes to have a +1 charge. So we have sodium with a +1 charge combining with sulfate with a -2 charge, and we know that our charges always need to add to 0. So that means that the formula for sodium sulfate must contain 2 sodium ions for every 1 sulfate ion. So we write that with a subscript of 2 after the sodium to indicate that there are 2 sodium ions here, and 1 sulfate, and we include the SO4 because that is the formula of the sulfate that we got from our list. So then calcium nitrate. Calcium is in group 2 on the periodic table, so those like 2+ charges. Nitrate we can find on our list is NO3 with a -1. So when we go to combine these, we've got a similar situation, but going in the opposite direction here, that we have 2 positives on our calcium and we only have 1 negative on our nitrate. So we're going to need 2 nitrate ions for every 1 calcium. Now, you'll notice we kind of have a problem. If I just put a 2 here, this now looks like there are 32 oxygens, which is not what we want. So what we have to do whenever we have more than one of a polyatomic ion in a formula is we enclose the polyatomic ion in parentheses to indicate that there are 2 of this entire grouping. So the parentheses, just like in math, are functioning as a grouping symbol here, that we're saying this subscript of 2 is now applying to this entire group of atoms inside the parentheses. So when there is more than one of a polyatomic is the only time that you use parentheses. So you need parentheses with the subscript after. Oops, sorry. So that's the one little tweak to how we write formulas when polyatomics are involved, and again, it's only when you have more than one of the polyatomic. So we didn't need the parentheses up here at all, because sodium is monatomic, so the 2 is applying just to the sodium, and we don't need anything special to indicate that. And we only have one of this grouping of atoms, so we don't need parentheses if there's not going to be anything after it. So that's kind of the one tweak where polyatomic formulas can be a little bit different, but other than that, it all functions exactly the same.